Okay, in this video we're going to talk about Unit 3, Objective 2, Integration by U-Substitution. U-Substitution is going to be how we deal with our chain rule for anti-differentiation. So if you remember our chain rule, the derivative of a composite function is going to be f prime of g of x times g prime of x. Now if this is the derivative of a function and we want to work backward to get to what the function was, we need to find that relationship between g and g prime. So you'll notice in what we have up here, we have a function inside the parentheses of f, and its derivative is outside the parentheses of f. So if we have what appears to be a product rule, or a product within our integral, we might be looking at the chain rule going backwards. So what we're going to try to find when we see a product is, do we see the derivative of another piece of the function inside our antiderivative? So what we're looking at is if we have something like the antiderivative of x squared sine x to the third. With respect to x. Actually, for this first one, let's make it 3x squared, and we'll deal with what happens if that 3 is not there in a minute. So we have 3x squared sine x to the third dx. So we see a product. We have the 3x squared, and we have the sine x cubed, so we know we have a product. So what we need to look at, since we don't have a product rule, is there the derivative of a function, or is the derivative of the function inside the parentheses in my problem? So inside the parentheses we see an x cubed, and outside the parentheses we see 3x squared. So we know that the derivative of x cubed is 3x squared, so we have a chain rule situation, we have a U-substitution situation. So U-substitution, we have to do exactly what it sounds like. We need to substitute something that we're going to call u into our antiderivative. So what we want to do is we want to take that function that's inside, we want to take that g of x from our chain rule, and we want to call that u. So in our problem here, we're going to say u is x to the third. Now we want to find the relationship between du and dx. So if we take the derivative of the left side, du, the derivative of the right side is going to be 3x squared dx. So we have this relationship with u and du, the derivative of u, the derivative of x cubed, and now we need to make that substitution. So if we think about our original problem, we can rewrite it to say sine of x cubed times 3x squared dx. So we can just kind of take that 3x squared and move it to the other side of the sign, so the 3x squared dx is by each other. The reason we want to do that is just to make the substitution a little bit more clear. We don't actually have to rewrite that, but if we look at this relationship here, u is equal to x to the third, we can make that substitution right here. And if we look at this relationship, du is equal to 3x squared dx, we can make that substitution right here. So we have the u that we want to substitute in. We have the du now that we want to substitute in. So this problem is going to turn into the antiderivative of sine of u du. And that's just something that we know the antiderivative of, or we should know the antiderivative of. The antiderivative of sine is negative cosine of u plus c. Now, our problem was written in terms of x. It's an antiderivative. Our answer right now is in terms of u. We don't really want that. We want to substitute the u back in. So our real answer is negative cosine of x to the third plus c. So we want to find the inside function, see if its derivative is inside, and make this substitution. Now I alluded to the fact that the 3 right here could be missing, and there's a way to deal with that. So let's look at this same problem, but let's take that 3 out of the problem. Let's make it just x squared sine x cubed. So if we just have x squared sine of x cubed with respect to x, we still see that we have inside an x to the third, and we see almost its derivative right here with x squared. We know that it's going to be missing that 3. The 3 is not going to be an issue. So if we set up that u substitution, the same one we just had, and say u is equal to x to the third, du would be equal to 3x squared dx. So if we look in our problem, we can see that we have an x squared dx in our problem. In our u substitution, we have an x squared dx. So if we need to get that x squared dx by itself so we can make the substitution, all we need to do over here is divide by 3. So we can say 1/3 du equals x squared dx. So we're trying to get that x term and the dx term to match. The constant 3 doesn't really matter. So now we can make that same substitution we did in the last one. So we can say that green yellowish x squared dx is going to turn into a 1/3 du, and our sign is just going to be of u. So sine of u times 1/3 du. And if you remember our rule from the first video, we are allowed to take this 1/3, since it's just a constant and it's multiplied by everything. We can bring that out front, and we're going to bring that out front every single time. So we have 1/3 times the antiderivative of sine of u du. Antiderivative of sine is negative cosine of u plus c. We still have that 1/3 multiplied, so let's make it negative 1/3 cosine of u plus c. Put your u back in, so negative 1/3 cosine of x to the third plus c. And if you want to make sure that you did this correctly, you can always take the derivative of your function. If you take the derivative of negative 1/3 cosine x cubed, you are going to end up at x squared sine of x to the third. So I'll leave that to you if you want to check it. We're not going to do that in this video. There's one more thing we do need to talk about, and that's taking a definite integral as opposed to taking an antiderivative with our u substitution. So let's look at the problem, say the integral from 1 to 2 of 2x times the square root of x squared plus 3 with respect to x. So just like derivatives, we want to get rid of our radicals before we do anything else. So the integral 1 to 2 of 2x times the quantity x squared plus 3 dx. So we see parentheses, we see a product, we think our u substitution. So inside the parentheses, oh, I forgot my 1/2 power to the 1/2. We see our parentheses, we see the inside, we see a potential u being x squared plus 3. We look for x squared plus 3's derivative. We see it right here. So we know we have a candidate for u substitution. So let's go ahead and make that substitution. We're going to say u is equal to x squared plus 3, which means du is going to be equal to 2x dx. So we can rewrite our problem as u to the 1/2 du. So the 2x dx turns into a du, the x squared plus 3 turns into the u. Now the issue is our limits of integration. We're integrating from 1 to 2, and if you think about what the integral means, The integral means the area under the curve from one x value to another. So if we think about a picture, and this is just going to be a general function, it's not going to be the function we're actually looking at. But if we have some function here, and we're integrating from a to b, we're integrating from this x value a to this x value b, and we're trying to find that area under the curve. So if we're looking at the problem we're at now, this 1 and this 2 are both x values. But if we look at our integral now, we have u is our variable. So we need to take into account the fact that we're using u instead of using x's, and we need to change those to be u values. The trick to making those x values is this relationship here, where we have u and x related to each other. So we can turn our upper limit of integration into a u value simply by taking that 2, plugging it into that relationship, and getting 7 for our upper limit of integration. Our lower limit, we do the same thing, and we get 4 for our lower limit of integration. So now we are going to do our fundamental theorem of calculus. So we're going to find the antiderivative. We're going to find capital F of u. So this one's kind of fun. We get to say fu to this problem. We increase our exponent from 1/2 to 3/2. Divide by 3/2 is the same thing as multiplying by 2/3. So if we evaluate that from 4 to 7, that's going to be capital F of 7 minus capital F of 4, which is going to be 2/3 times 7 to the 3/2 minus 2/3 times 7, I'm sorry, not 7, but 4 to the 3/2. And I will leave that simplification up to you. But the trick is on our definite integration, we need to change our x limits into u limits. And the other thing that I want to point out, since we turned these into u values, when we took our antiderivative, we did not go back to x like we did in the antiderivative. If we're getting a numeric value for our answer, that's all we care about. We don't need to go back to x like we did on the other problems because we started with x there. Now we started with x and we ended with x. Now we're starting with x and we want to end with a number, so we don't need to go back to x. So that'll do it for this video. We'll see you in the next one.